Okay, now, so ito na yung last topic. Introduction to cryogenics. Kasi yung cryogenics is a separate subject na yan. Introduction lang tayo. So, parts naman ito is, meron tayong mga heat exchanger, expander, liquid, compressors, and kung ano-ano pa magiging itsura nito later sa lecture natin. Cover lang naman to eh. So, cryogenics is a term normally associated with low temperatures. However, the location on the temperature scale at which refrigeration generally ends and cryogenic begins has never been well defined. So, yan ang may boundary yan eh. Most scientists and engineers working in this field restrict cryogenics to a temperature below 125 K because the normal boiling points of most of the permanent gases, that is helium, hydrogen, neon, nitrogen, argon, oxygen, and air, occurs below this temperature. And contrast, most of the common refrigerant have boiling points above this temperature. So yan, ang common kasi sa vapor compression is yung mga refrigerants. Dito naman sa refrigeration, kaya dito ang ginawang boundary. Yung mga sa cryogenics, iba dyan yung mga, ito na yung mga gases. Cryogenic engineering, therefore, is involved with the design and development of low-temperature system and component. So in such activities, the designer must be familiar with the properties of the fluid used to achieve these low temperatures as well as the physical properties of the component used to produce, maintain, and apply such temperatures. Yo, punta kayo sa Paris Handbook o sa internet, may mga online na dyan ng mga properties ng ito, mga fluid. Okay? Neon, nitrogen, argon, at low temperature, meron silang mga value. Enthalpy, pressure, etc. So, general application. The application of cryogenic engineering has become extensive. So, in the United States, for example, nearly 30% of the oxygen produced by cryogenic separation is used by the steel industry to reduce the cost of high-grade steel, while another 20% is used in chemical process industry to produce a variety of oxygenated compounds. Liquid hydrogen production has risen from laboratories quantities to a level of over 2.1 kg per second. Similarly, liquid helium demand has desired the construction of large plants to separate helium from natural gas by cryogenics. Okay, so the demand for energy likewise have accelerated the construction of large baseload liquefied natural gas (LNG) plants. Some of the current applications include the development of high-field magnets and sophisticated electronic devices that use the phenomenon of superconductivity of materials at low temperatures. So space simulation requires cryopumping, the freezing of residual gases in chamber on cold surface to provide the ultra-high vacuum representative of conditions in the space. This concept has also been used in commercial high vacuum pump. Okay, yung mga cryogenics, mechanical. So, kaya lang, common lang sa ating mga nag-design dito is mga air S-box, sprinkler, puro piping. So, pagdating dito sa mga equipment, bira. Okay, so the food industry, yan, uses large amount of liquid nitrogen to freeze the more expensive food like shrimp and to maintain frozen food during transport. So liquid nitrogen cooled containers are used to preserve whole blood, bone marrow, and animal semen for extended period. Cryogenic surgery is performed to cure such involuntary disorder as Parkinson's disease. Yan. Medical diagnosis uses magnetic resonance imaging, MRI, which requires cryogenically cooled superconducting magnet. Finally, the chemical processing industry relies on cryogenic temperatures to recover the more malleable heavy components or upgrade the heat content of the fuel gas from natural gas, to recover useful components like argon and neon from air, to purify various process and waste stream, and to produce ethylene from a mixture of olefin compounds. Siguro nasa ano na to, chemical engineering mostly. Okay, no, kasi baka kukulin nga nito si chemical processing industry. So, sa chemical is process lang eh. Ewan ko kung inaano pa nila yung equipment. Low temperature properties. Test data are necessary because properties at low temperature are often significantly different from those at ambient temperature. For example, the phenomenon of superconductivity, the vanishing of specific heat, and the onset of ductile brittle transition in carbon still cannot be inferred from property measurement obtained at ambient temperature. Refrigeration and liquefaction. A refrigeration or liquefaction process at cryogenic temperature usually involves ambient compression of a suitable fluid with heat ejected to a coolant. During the compression and cooling process, the enthalpy and entropy of the fluid decrease. At the cryogenic temperature, where heat is absorbed, the enthalpy and entropy of the fluid increase. The reduction in temperature of the process fluid is usually accomplished by a heat exchange with a returning colder fluid and then followed with an expansion of the process fluid. This expansion may take place using either throttling device approximating an isenthalpic expansion with only a reduction in temperature, or work-producing device approximating an isentropic expansion in which both the temperature and enthalpy are decreased. Normal commercial refrigeration generally uses a vapor compression process. Temperature down to about 200 K can be obtained by cascading vapor compression processes in which refrigeration is obtained by liquid evaporation in each stage. Below this temperature, isenthalpic or isentropic expansion are generally used either singly or in combination. With few exceptions, refrigerators using this method also absorb heat by vaporization of the liquid. If no suitable liquid exists to absorb the heat by evaporation over a temperature raise, a cold gas must be available to absorb the heat. So this is generally accomplished by using work-producing expansion engine. In a continuous process, refrigeration process, no refrigerant accumulates in any part of the system. This is in contrast with liquefaction system, where liquid accumulates and is continuously withdrawn. So may in and outs. Thus, in liquefaction system, the total mass of the returning cold gas that is warm prior to the compression is less than the mass of gas that is to be cooled, creating an unbalance of flow in the heat exchanger. In a refrigerator, the mass flow rate of the warm and cold gas stream in the heat exchangers are usually equal, unless a portion of the warm gas flow is diverted to a work-producing expander. This condition of equal flow is usually called balance flow condition in heat exchanger. So wala tayong anong figure dito kasi wala rin yung reference natin. So next is isenthalpic expansion. This is the schematic diagram, and yan, ng equipment, apparatus, and be it temperature entropy diagram. This is called the simple Joule-Thomson cycle refrigerator. Okay. Thermodynamic process identified either as the simple Lindy cycle or the Joule-Thomson cycle. Common na tawag dito is Lindy. Okay. GT cycle is shown schematically in figure 1. And this cycle, the gaseous refrigerant is compressed. Yan, compressor. Isothermally. 1, 2, 3, 4. Ito yung refrigerant mo. Compress isothermally at ambient by rejecting heat to the coolant. So ito yung coolant. Any coolant yan. Water, compressor yan. To tube. Compressor system yan. Ito may coolant. Okay? Isang package na yan. 1 to 2. The compressed refrigerant is then cooled in a heat exchanger with cold gas streaming returning to the compressor intake. Yan. Compressor hot. So cold gas, nagbabalik naman doon. So heat exchanger siya, di ba? So Joule-Thomson cooling accompanying the expansion of the gas exiting the heat exchanger further reduced the temperature of the refrigerant under steady state condition. A small fraction of the refrigerant is liquefied. For a refrigerator, the liquid fraction is vaporized by absorbing the heat Q that is to be removed combined with unliquefied fraction, and after warming in the heat exchanger, return to the compressor. Figure 1b shows the ideal process on a temperature entropy diagram. So ito yan. Yan, di ba? Tapos pabalik doon. So ito kasing curve, sa ideal gas, dito lang siya. Dito, pag sa cryogenic, papasok na sa TS diagram yung mga gas niya. So, yan ang yung diagram niya. Okay? So, applying the first law to this refrigeration cycle by assuming no heat leaks to the system as well as negligible kinetic and potential energy changes in the refrigeration fluid, the refrigeration effect per unit mass of refrigeration is simply the difference in enthalpies of stream 1 and 2 and figure 1a. Thus, the coefficient of performance COP of the ideal GT cycle or Linde cycle is given by COP is equal to Q over W or H1 minus H2 divided by T1 times S1 minus H2 minus S1 minus H2. Yan. This is the available energy. Q is the iba S minus TS. Yan. Where Q is the refrigerating effect, W is the work of compression, H1 and S1 are the specific enthalpy, and entropy at 1 and S2 and 2, the specific enthalpy and entropy at point 2, figure 1a. Kasi yung change of enthalpy noon, nito, yun din ang change of enthalpy niyan, kung tutusin. Diba? Tama. Ano yung enthalpy nitong 3, saka 4 and 5, ganun din yun. Kasi ito S1, so nag-change doon, bumaba. Ito, nag-cool. Ito, tumaas. So, ano yung man difference nun? Yun din ang difference nito. Kasi yung mass flow, isa. Okay? Check nyo lang. For a liquefier, the liquefier, dito yan, portion is continuously withdrawn from the liquid reservoir. And only the unliquefied portion of the liquid is warmed in the heat exchanger and returned to the compressor. The fraction Y that is liquefied is determined. So ito ba na yan? The fraction Y determined by applying the first law to the heat exchanger GT valve liquid reservoir is Y is equal to S1 minus H2 over S1 minus SF. So S1, H2, ganun din siya. Where SF is the specific enthalpy of saturated liquid being withdrawn. So dito mawi-withdrawn siya. May withdraw dyan. The maximum liquefaction occurs when the difference between H1 and H2 is maximized. So to account for any heat leak QL into the system, equation needs to be modified. So yan. Y is equal to S1 minus S2 minus QL over S1 minus SS, resulting in a decrease in the fraction of liquefied. The work of compression is identical to that determined from the GT refrigerator. The figure of merit, FOM, another term, than COP, so iba naman to. FOM is defined as W over MFI divided by the weight over MF, or where W over MF1 is the work of compression per unit mass liquefied for the ideal liquefier, and one is the work of compression per unit mass liquefied for the GT liquefier. So ito na yon. The FOM reduced to T1 times S1 minus SF minus H1 minus SF over T1 over S1 minus S2F minus, H1 minus H2, then S1 minus S2 over S1 minus SF. So may mali dito tayo. Sige ko lang to. This is S2. Okay, so ito na yung figure of merit. Yeah, sinetang ko lang S2. Okay. Then, liquefaction by this cycle requires that the inversion temperature of the refrigerant be above ambient temperature to provide cooling as the process is initiated. Auxiliary refrigeration is required if the GNT cycle is to be used to liquefy fluid whose inversion temperature is below ambient. Hindi na kaya. This condition occurs when liquefaction of helium, hydrogen, and neon is attempted. Liquid nitrogen is the optimum auxiliary refrigerant for hydrogen and neon liquefaction system, while liquid hydrogen accompanied by liquid nitrogen are the normal auxiliary refrigerant for helium liquefaction system. For the diagram, so check nyo lang yung mga planta. Upper operating pressures for GT cycle are often as high as 20 megapascal. Upper operating pressures. Saan yung upper? Ito. O compress mo. So, ito yung upper pressure niya. So, to reduce the work of compression in the previous cycle, so ito naman, pag-reduce ng work of compression para tumaas yung efficiency o the COP. A two-stage or dual pressure cycle, ito, may be used in which the pressure is reduced by two successive isentropic expansion as shown in figure 2. So, kaya na mag-ano yan. Ito yung first expansion and second expansion. Ito, pumasok doon, pumas doon. Ito naman dyan. Ito, dito, yan. Ganyan ang cycle niya. Since the work of compression is approximately proportional to the logarithm of the pressure ratio, di ba yung natural log? And the Joule-Thomson coefficient cooling is roughly proportional to the pressure difference. Compression work reduces more than refrigeration performance. Hence, the dual process produces the same quantity of refrigeration with less energy input than the GT process. Yan ang tsura niya. Ito, si substitute dito, single siya nagbabala. Tapos, ito nandun. Yung isang part nandun. Yan. Okay. Diagram yun na lang yan. So, the theoretical liquid yields for the dual pressure GT cycle is obtained by making energy balance around the cold heat exchanger, lower JT bulb, and liquid reservoir is as follows. So, ito na-derive to dyan. Y is equal to H minus HT over S minus HF minus MI over M times HI minus H2 over S minus HF. MI yan. So, madiderive nyo naman yan later pag nasa cryogenics na kayo. Ano pa lang tayo? Introduction. Where M, MF, and MI are the mass flow rate of the stream designated on figure 2. 2. So, the intermediate pressure in this cycle must be optimized. For a cylinder with an upper pressure of 20 megapascal, the intermediate optimum pressure generally occurs 3 to 6 megapascal. Next, isentropic expansion. Isentropic expansion naman tayo. So, I think isentropic, because the temperature always decrease in a work-producing expansion, so di na bago, tama. So, wala itong tawag, isentropic lang. Because the temperature always decrease in a work-producing expansion, cooling does not depend on being below the inversion temperature prior to expansion. In large industrial refrigerator, the work produced during expansion is conserved. So, wala kang makikita ng saturation curve yan. So, in a small refrigerator, the energy from the expansion is usually dissipated in a gas or hydraulic pump or other suitable device. This is a gas. A schematic of a refrigerator using work-producing expansion principle and the corresponding temperature entropy diagram are shown in figure 3. So, yan. 1, 2 compressor is constant temperature. 3 to 4 expansion engine, constant enthalpy. Constant, entropy. Constant entropy nga. Yan. So, gas compressed isothermally at ambient temperature and is cooled in heat exchanger by gas being warmed on its return to the compressor intake. Further cooling takes place in the expansion engine. In practice, this expansion is never truly isentropic as shown by Part 3 and 4 on the temperature entropy diagram. So tawag lang is isentropic. The refrigerator produces a cold gas that absorbs heat during the path 4 to 5 and provides a method of refrigeration that can be used to obtain temperatures between those of the boiling points of the lower boiling cryogenic fluids. The coefficient of performance of an ideal gas refrigerator with varying refrigerator temperature can be obtained from the relation COP is equal to T5 minus T4 over T1 times ln of T5 over T4 minus T5 minus T4. Yan. Asymptotic to nakukuha. Constant temperature 4 and 5. Constant pressure. So where the absolute temperatures refer to the designated points shown in figure 3 and T1 is the ambient temperature. Combined isentropic and isentropic expansion. To take advantage of the increased reversibility gained by the use of work-producing expansion engine, while at the same time minimizing the problems associated with the formation of liquid in such a device, Cloud developed a process that combined both expansion processes in the same cycle. A schematic of this cycle along with the corresponding temperature entropy diagram is shown in figure 4. Ayan, combined na siya. Ito yung may expansion engine, gusto yung may expansion valve. Diyan, top sa 3, then punta doon sa ano. Diba? Tapos siya. Tapos ito naman sa liquid reservoir, ito. So ito na yung cycle mo, ito yung tinap. An energy balance for this system which incorporates the heat exchanger, the expansion engine GT expansion valve, and liquid reservoir permits evaluation of the refrigerating effect or in case of a liquefier allows evaluation of the liquid yield. Yield is yung Y. For the refrigerator, the refrigerating effect is Q is equal to M times H1 minus H2 plus ME times H3 minus HE. Where ME and HE are the mass rate flow through the expander and the specific enthalpy of the steam leaving the expander. So, yung E, 3, HE, ito. Daming heat exchanger. Yan. So, for a liquefier, the energy balance yields H3 minus M times H2 minus M minus MF H1 minus ME times H3 minus HE minus MF SF all 0 equals 0. Collecting terms and using previously adapted symbol give the liquid fraction obtained as Y is equal to S4 minus H2 over S4 minus SF minus ME over M times S3 minus HC over S1 minus SF. Okay? For detailed derivation nito, so check nyo na lang. For non-ideal expander, the HE term would be replaced by HE prime. One modification of the Cloud cycle that has been used extensively in high-pressure liquefaction plant for air is the Hayland cycle. In this cycle, the first warm heat exchangers, iba pala to, and in this cycle, the first warm heat exchanger in figure 4 is eliminated, thereby allowing the inlet of the expander to operate at ambient temperature. So, mawawala to. Which minimizes many of the lubrication problem that are often encountered at lower temperature. Yeah. So, other modifications of the basic Cloud cycle are the use of wet expander operating in the two-phase region to replace the throttling valve and the addition of saturated vapor compressor following the liquid refrigerant. The two-phase expander is used with system involving helium as the working fluid because the thermal capacity of the compressed gas is, in many cases, larger than the latent heat of the liquid phase. So experience has shown that operation of the expander with helium in the two-phase region has little effect on the expander efficiency as experienced with expander handling either nitrogen or air. The addition of the saturated vapor compressor actually improves the thermodynamic performance of the system. So, ibig sabihin nagkaroon ng mga specialty per, ano to, fluid, helium o per gas. So, another modification of the basic cloud cycle is the dual pressure cloud cycle. So, similarly in principle to the Lindy dual pressure system, dual pressure system shown in figure 2. So, yan din. Nagkaroon siya ng, ano lang, expansion engine. So, this is figure 2. So, hindi ito, ano. So, wala siyang figure. So, basta ito na. Ito, dagdagan mo lang ng, ito lang idadagdag mo doon sa taas. Okay? So, in this dual pressure cycle, only the gas that flows through the expansion valve is compressed to high pressure. This reduces the work requirement per unit mass of liquefied. So, kayo na mag-revise ng diagram. Ballon in 1985 compared the cloud dual pressure cycle with the Lindy dual pressure cycle and showed that in the liquefaction of air, the liquid yield can be doubled while the work per unit mass can be have when the cloud dual pressure is selected. Still, another extension of the cloud cycle is the Collins helium liquefier. Depending on the helium inlet pressure from 2 to 5 expansion engine are used in the system. Okay, dami. The addition of a liquid nitrogen pre-cooling bath results in a 2 to 3-fold increase in liquefaction performance. Okay? So, mga basic pala kasi isa, dalawa, tatlo. Pag abot ng, yan ang actual yung makikita mo na yung mga diagram nyo, ang lalaki na. Okay? Parang electronics na. So, mixed refrigerant cycle. To. So, with the advent of large natural gas liquefaction, so to sa LNG production. The mixed refrigerant cycles. This cycle in principle resembles the cascade cycle occasionally used in LNG production as in figure 5. After purification, the natural gas stream is cooled by successive vaporization of propane, ethylene, and methane. Yan to. Diba? Coolant. Separate. 1, 2, 3. So, madali lang. So, yan, natural gas feed na. LNG. These gases have it's been liquefied in conventional refrigerant loop. Each refrigerant may be vaporized at 2 or 3 different pressure levels to increase natural gas cooling capacity, but at a cost of considerably increased process complexity. Masyado malamig kasi yan. So, yan, reduce, then reduce nyo naman to. Yan. Pababa ang temperature. Cooling curves for natural gas liquefaction by the cascade process are shown in figure 6A and 6B. Yan, yung mga refrigerant, C1, C2, so yan. The cascade cycle efficiency can be improved considerably by increasing the number of refrigerant used. For the same flow rate, the actual work required for the 9-level cascade cycle is approximately 80% of that required by the 3-level cascade cycle. This increase in efficiency is achieved by minimizing the temperature difference throughout the cooling curve. So the cascade system, ito yung A, 3-level, B, 9-level cascade cycle cooling curves for natural gas. can be designed to approximate any cooling but is the quantity of refrigeration provided at the various temperature levels can be chosen so that the temperature differences between the warm and cooling stream in the evaporator and heat exchanger approach a practical minimum. Smaller temperature difference equate to lower reversibilities and therefore lower power consumption. And the simplified version of the mixed refrigerant cycle shown in figure 7. Ito yung gas speed, then compressor, pasok dito. Ito yung gas speed nyo, series, to LNG storage. Ito naman yung mga iba-ibang sistema. Oop, 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 oop. So this version involves circulation of a single mixed refrigerant system which is repeatedly condensed, vaporized, separated, and expanded. Yan. Separated, cooled dyan. Single refrigerant. Okay. As a result, such processes require more sophisticated design approaches and more complete knowledge of thermodynamic properties of gaseous mixtures than expander or cascade cycles. Nevertheless, simplifying compression and heat exchange in such cycle offers potential for reduced capital expenditure over conventional cascade system. Note the similarity of the temperature versus enthalpy diagram shown in figure 8 for the mixed refrigerant cycle with the corresponding diagram for the 9-level cascade cycle of friction B. So, yeah, similarity. So, proprietary variation of the mixed refrigerant have developed the technology. In one commercial process, for example, the gas mixture is obtained by condensing part of the natural gas feed. This has the advantage of requiring no fluid input other than natural gas itself. On the other hand, this procedure can cause a slow start-up because of the refrigerant that must be collected and the time required to adjust its composition. Another version uses a multi-component refrigerant that is circulated in a completely separate loop. The mixture is prepared from gaseous component to obtain the desired composition. Thereafter, only occasional makeup gases are added, usually from cylinder. This process is simpler and allow for rapid startup. On the other hand, the refrigerant mixture must be stored when the process is shut down. Accordingly, suction and source dam must be provided with a resulting increase in capital expenditure. So Gomer represents a good review of mixed refrigerant cycle. Example. So this is from thermodynamics by Peirce. Kita niya? So the Linde process is used to manufacture dry ice, solid CO2, item B31. The CO2 vapor enters the compressor at, tingnan niyo yung figure, 15 PSI, A, and 80 Fahrenheit. And after 3 stages of compression, isa lang compress natin pero sa 3 stage yan. With negligible pressure drop during intercooling, it leaves 800 psi. Between stages and in intercooling, the CO2 is cooled back to 80 Fahrenheit by cooling water. The compressor efficiency for each stage is 70%, leaving the aftercooler at 80 Fahrenheit. The CO2 passes through a regenerative heat exchanger. Okay. So, mamaya tingnan natin yung ano yung naka-enclose na yan. Throttles 3 to 4 to 1 at ATM. Yan, 3 to 4 sa baba, figure. So, the solid is removed from the receiver. So, the vapor returns through the heat exchanger, leaving it at 70 degrees Fahrenheit. So, with makeup and heat, it enters the compressor at 80 degrees Fahrenheit and the cycle repeats. Steady state operation. No heat except as mentioned. Compute A, the fraction of solid CO2 obtained. B, the state at entry to the expansion valve. So, Energy balance. C, the adiabatic work necessary for 1 pound and for 100 pound per minute of solid. Let the works be per stage be approximately the same. Yan. Okay. So dito show na mas maraming compressor yan. So wait na. So ito lang. Putol pa. Ito yung 1, 2. Diagram mo, this is constant, di ba? Ang linear process is constant temperature. Ito, may process to. Compressor na, sabi dyan, 3-stage compression with negligible pressure drop during intercooling. It leaves 800 psi. Between the stages and in the aftercooler, to yon, the CO2 is cooled back to 80 Fahrenheit. So, yung system na yan is 1 to 2 is bumalik sa ating temperature. So, considered as constant temperature. Pero may sarili siyang process dito na may makukuha kang work. Andyan, mamaya. So, this is now a linear process. So, ang efficiency dito sa ang compressor efficiency is 70%. So, sa loob na ng compressor yan. Ha? So, throttling 3 to 4. Sa heat exchanger, delta P is approximately 0. So, walang pressure drop dyan. So, 3 to 4 is to 1 atmosphere. Figure 17-6. Solid is removed to from receiver. So, dito. Ayan yung na-remove mo. 3 to 4. So, pagdating sa 4, so may na-remove ka. Yung na-remove mo yan, iyan ang makeup mo. Yan. It enters the compressor 80 Fahrenheit and the cycle repeats. Okay? No heat except as mentioned. So, what is the fraction of solid CO2 obtained? Ito. And the balance adiabatic work necessary for 1 pound and 100 pound per minute of solid. So, mamaya makita natin yan. So, given is the Lindy process, dry ice. CO2 is dry ice, di ba? Compressor at 15 psi and 80 Fahrenheit. Three-stage compressor intercooling leaves at 800 psi. Cold back to 80 Fahrenheit. Regenerative heat exchanger, leaving at 70 Fahrenheit at stage B. Ito. Stage B. Wait, stage 3 yata to. Okay. Wait. So ito yung given nga. Required fraction of solid CO2 obtained. B, the state at entry to the expansion valve. Show energy balance. C, adiabatic work necessary for 1 pound and for 100 pounds of solid. Letter B, ano ito ba yun? So, ito pala is state 7, hindi sa state 3 or state B. Yeah. Okay. Vapor returns through the heat exchanger, leaving it at 70 Fahrenheit. So, yan, leaving, di ba? Punta doon. Okay. So, A, the fraction of solid CO2 obtained. CO2 item B31, nung first na book, andun yung mga properties ng CO2. Ano doon. At the state 1, 15 PSIA, 80 Fahrenheit. X1 is 169.65 BTU per pound. At the state 2, 800 PSIA is 80 Fahrenheit. Is H2 is equal to 138.41 BTU per pound. Hindi ko alam kung graph yata to o tabulation. So, para makuha mo yung exact value, so gumamit ako ng online na stable na malapit doon sa value doon sa figure. Okay? Sa chart. Yan. Kaya nakuha to. Kasi kung doon ka ba sa chart, hindi mo makukuha itong mga decimal places na yan. Okay? S2 is 138.41. At state 1, atmosphere is H6 is 134.5 BTU per pound. H5 is negative 116 BTU per pound. Okay? Sa chart kasi, hindi mo makuha yung eksakto. So at 15 PSIA, 70 Fahrenheit, H7 is equal to H1, is 167.62 BTU per pound. So H2 is equal to H7 times 1 minus Y plus H5 times Y. So Y is equal to H7 minus H2 over H7 minus H5 is equal to 167.62 minus 138.41 over 167.62 minus negative 116.5 is 0.1028 yung fraction. Okay? Kasi nga yung makeup mo is equal to ito. Ano ba yun? So consider mo to as a whole. Yan, as a whole. So energy balance mo to. Nung buong to, energy balance mo yan. H2. Ito out. H2, ito lang ang papasok. So ito out, ito out. So yan lang ang balance mo. So H7 times 1 minus Y. Kasi wala pa yung makeup mo, di ba? So 1 minus Y. So ito yung Y mo. So Y times H5. Yan. So makuha mo yung Y dyan. Okay? Wala ka nakitang 3, 4, 6 kasi ito ang binuo natin na energy balance. Yung buo niyan. Yan. So makuha mo yung Y. Technique lang yan. Kasaka ito. So yung web NIST yata, meron doon yung mga check nyo yung value doon sa figure para lumapit ka din dito sa item B31. Okay? Baka iba yung reference nun. So, maghanap ka ng iba. Marami kasing basis yung mga enthalpy. So, B, state at entry to the expansion valve. Yan, ito. What is this? So, show energy balance. Energy balance is H2 minus H3 times 1 minus Y times H7 minus H6. So, meron tong H2, H7, H6, and Y. Nakuha mo na. So, 138.41 minus H3 is equal to 1 minus 0.1028 times 167.62 minus 134.5. So, H3 is equal to 108.69 BTU per pound. Then at P3 is equal to 800 PSI, T3 is 63 Fahrenheit. So this is now the answer. Okay. With pressure 800 PSI and enthalpy of 108.69, ang temperature mo nun sa table o sa graph, sa chart properties is 63 Fahrenheit. At doon din, makukuha mo yung SF3 is 59 BTU per pound and HGT is 130.5 para makuha mo yung quality. Kasi dito, kailangan mo dito, siyempre, sasabay mo yung quality. Hindi lang pressure. Nakuha mo yung S3, ang kailangan mo dito is pressure, temperature. Ano yung quality mo? Okay? Kasi saturation curve yan. So, X3 is, ayan, 108.69 minus 59 over 130 minus 59 is 0.7 is 70%. Okay? Kaya di sabihin, automatic yun. Pag nasa wet region ka, hindi lang pressure, temperature. Kung sabihin, mahaba pa yung value mo. Okay? Saka hindi enthalpy ang binibigay, kundi pressure and temperature plus yung quality. Pressure or quality. So yan, 70%. Then, the adiabatic work necessary for 1 pound and for 100 pounds per minute. So, this is a 3 stage. So, kunin mo yung unang stage, times 3 mo na lang yung work. Okay? Yung unang stage for optimum pressure, yung parang sa 2 stage, ito, 2 stage square, ito cube root. So, P sub I1 is the cube root of P sub I squared times P sub 2. Yan. So, is equal to the cube root of 15 squared times 800 is 56.5 PSI. Ito yung first discharge ng compressor sa stage. Compressor. Discharge ng first stage compressor 56.5 PSI. Okay. in-square mo tong ano. Pag second discharge, itong PI, ito naman ang i-square mo. Okay? Pag final discharge, wala ka ng problema. Pito na lang yun. Okay? So, at state 1, 15 PSI, 80 PSI. So, S1 again, 169.65 BTU per pound. S1 is 0.495 BTU per pound ranking. So, carbon dioxide to So, at state I, so SI is equal to ito, 206.77 BTU per pound, 56.5 PSI. S2 is equal to S1. Yan. Ang hanapin mo doon is yung 56.5 tapos yung entropy na 0.495, makukuha mo yung properties na 206.77 BTU per pound. Okay? So, pag chart nga, siguro magtama yung tuldok mo doon. So, mas maganda by numerical value na sa hanap ka ng makakakuha ng accurate. So, work is 3 times HI minus S1 kasi 3 stages. Kinuha mo lang naman yung sa single stage equal na yung enthalpy nun. Is 3 times 206.77 minus 169.65 over 0.1025 over 0.7 is 1552.06 BTU per pound. Okay? Why? This is the efficiency. Ito ideal to. So, divide ka ng 0.7. Bakit dinivide mo ng Y? So, ito yung fraction ng bakit yan ma'am ng Y? Okay? Ano kasi dito, ang ano dito is 1 pound of solid na na-collect mo. So, i-divide mo siya ng Y. So, ibig sabihin, yan na yung mass ng carbon dioxide na nag-iikot dito. Kasi ito yung ano mo, M. Ang tawag doon? 1 over Y mo, ito. 1 over Y. 1 over Y, 1 over Y. So, multiply mo ng Y. So, magiging 1 na lang to. 1, 1. Multiply mo to ng Y. Isa ito, 1 over Y eh. Yung pasok dyan. Kasi a fraction nun is Y, sibaw. A fraction nun Y is so magiging Y to. So, ito, 1 over Y minus Y. Tapos, ito. So, this is for 1 pound there is 1 over Y. For 1 pound of product, there is 1 over Y pounds of carbon dioxide. Diba? So, that is, so ito nga is 1552.06 BTU per pound of carbon dioxide. Yan. Per pound of solids pala, solids. Okay. Yan. So, this is now 0.455 kilowatt hour per pound of solid. Ito yung answer kasi dun sa book. So, the work is 100 times 0.455. This is pounds per minute. So, of solid is 45.5 kilowatt hour per minute. So, this is the answer then sa book. So, okay na? So, this is the end of cryogenics. This is also the mga diagram makikita nyo sa internet yan. Yan, mga cloud liquefaction classes. Sa refrigeration. Kung doon naman sa power plant, sa mga alternative energy, meron namang magalito rin makita mong itsura. Yung mga, ano yon yung OTEC. Yan, OTEC naman yan. Okay?